Yeah. Right. So we actually have a tool that we could use to calculate currents in our circuit, right? So we could use current analysis, right? So in this case, then you know what the current is. So you don't need to assume any currents. Remember, for current, the loop analysis, we used to assume current direction, right? But in this one, you know the current direction. So you know phi one going in this direction, and you know phi two going in this direction, right? You know that. You don't need to assume that. You know it because you use the right hand screw to get the answer. Yeah? So from there, you have phi one, you have phi two, right? So what we could do now is basically do the loop analysis. And once we get the two equations, we could just solve them simultaneously for phi one and phi two. Yeah, and once you get phi one and phi two, the current or the flux through this branch here, which is basically the flux that going through the air gap, would have be a phi one plus the phi two. And that'll be the answer for the first part. And if you want the flux density, right, you have the equations that you could use to get flux density. And that is really the end of the question. Right, this question really just working down to this. Right, so let us go through quick. All right, so I'll do it on, see if I could zoom out. Right, I think that is enough space there. Right, so let me start with the phi one loop first, right? So remember, so this would be, we just assume everything to be positive, right? So that's like we did before, but it's a little different, right? So this one here would just be a phi one by RAFBE, right? So we're here now, then you go into this piece here, it would just be plus phi one RC. And remember, when you're going through, you notice that two currents going through this branch, right? But the only difference is compared to the loop analysis from 1000 is that the both currents go in the same direction. Yeah, both going down. They go and go up and contribute to the current or the flux in this branch. So they're not going like oppose each other. They go and come together to support. Yeah. So in this case, since everything going down in this branch here, it have no minus. So it doesn't have a flux going in the opposite direction. So luckily for us, that is why this one was simple, because everything will just be positive. Okay, it have nothing going against the current that you assume. Phi 2 going in the same direction with it coming down in this branch here. Phi 1, same thing. They both go and aid. It won't have any opposing currents going up here. Have none. Look at it, have none. Both of them coming down. Alright, so this one here will just be plus phi 2 RC. Alright, and then they go through RG. It'll be plus phi 1 RG. Then plus your phi 2 RG. Right, and all of that will just equal to your source, F1. Yeah, same thing as loop, but it's just one, you know the current directions already. Two, since in the branch it have no opposing currents, so it have no minus, everything will just be positive, right? So note to self, I assume everything to be positive. Basically, the voltage drops across the resistors to be positive. You could have assumed it to be minus, like what you're accustomed doing. It's just everything will just be minus. Yeah? Because everything aiding each other, nothing opposing or going in the opposite direction. All right. If you do that for phi 2, same idea. So the first piece is going up here. So it'll be phi 2 by R CBDE. All right. And then they go through here plus phi 2 RC plus phi 1 RC. And then go down for RG. It'll be plus phi 2 RG. And then plus phi 1 RG. And that is equal to F2. Yeah. Nice. And now what you could do now, maybe trying to get a simultaneous equation so you could factorize all the things that have phi 1 in it. So that'd be a RAFBE, which is this piece here, and the RC, and the RG. Right, and then you could factorize this stuff that have phi 2, which would be a RC and the RG. Right, and that is equal to F. Right, and the same thing for the second equation, factorize the stuff that have phi 2 in it. or you could like put it in phi 1, right? So it'll be easier to put the phi 1 under the phi 1, right? So phi 1's in this, the second one here, which is this one here. That will be RC and your RG. And for phi 2, you have RC BDE plus your RG and your RC. And that is equal to F2. Right? So you have two equations. The thing about these equations are, you have what these reluctances are. You have what F1 and F2. When you have, remember, you have what these things are. We already calculated on top, right? So when you plug in the values for the question, right? So you just plug in it in and you can just use your calculator to solve the two simultaneous equations, right? So let me just give you what they'll boil down to. So it'll be phi 1, or we can say 13.34 mega phi 1 and plus 10.76 mega, just beat by 10 to the 6, right? Phi 2, and that is equal to 5,000. Like 1, and then you have 10.76 mega phi 1 plus 13.34 mega phi 2, and that is equal to 5,000. And you call that the second equation. Yeah, and you just plug this in a calculator and solve, right? Or you could use whatever method you know to use to solve simultaneous equations, right? And you just end up with phi 1 equaling to 2.067 by 10 to the minus 4 webers, and ironically, I2 was equal to 2.067 by 10 to the minus 4. They were the same thing. Yeah. And now for the first part of the answer, that's like what we did on top. The flux going through the air gap, which is what I want, the air gap flux, would just be a phi 1 plus the phi 2. Because the fluxes aiding each other. Right? So you could call this phi G, phi 1 plus phi 2, which is just this multiplied by 2. Yeah, so you end up with 4.13 by 10 to the minus 4 others. Yeah, and then because I'm basically done. The second thing I wanted, so we get the air gap flux, the what the air gap flux density, right? So luckily for us, we have our equation for flux density. So we know phi is equal to B A. Yeah, so in this case, it'll be phi G is equal to BG, and you have AG. So we want B, so it does be BG, would that's equal to phi G divided by the cross-sectional area for the air gap, which we already have. So it's just 4.13 by 10 to the minus 4 divided by 4 centimeters squared. There's the same shape. Right, so you would just end up with 1.034 Tesla. All right, and the last thing the question asks for was the magnetic field intensity, which is H of the air gap. All right, so now our equation for H. All right, so B is equal to mu H, and in our case it will be BG is equal to mu 0, because mu 0 is mu G, and HG. So it does transpose for HG. You end up with BG and mu 0. It does calculate what BG is, and you divide it by your permeability of free space, which is BG, but sorry, mu G. And when you plug that in a calculator, you just get 0.822 by 10 to the 6 ampere turns per meter. Yeah, and that is the end of the question. And nothing else in the question, right? So the takeaways from the question, and it's a good question to practice, because it helps you with gaining lengths, breaking up the reluctances. This current loop thing, it catch real people. So what I say we would do is the same idea, It's just that the trick in this one is they already give you the assumed flux directions or current directions. So you had to use those current directions. And then everything will just aid each other. So we won't have any opposing fluxes. Right? And the equations are the same, any lengths, cross-sectional areas. Luckily for us, they were symmetrical. So one piece was equal to the other piece. Right? Um, they break it down into the currents, the loop analysis, solve it simultaneously. We notice that phi g, which is the flux through the air gap, which is this branch here, will just be the sum of the two fluxes. So you get phi 1 plus phi 2. You get phi g, and at that point there, plus you end up. Okay, have equations to get the flux density and the field intensity. Right? And that's that question.